Okay, this is the second video, and we are going to start at problem 34 on page 85. The book is in the description of the video. So we're looking for the limit as x approaches 0, square root of x to the third plus x squared times sine pi over x. We are looking for the limit of this function. So there are a lot of interesting things going on over here. The first is we need to understand what sine of, let's say, 1 over x is doing, because that is important. And what it's doing is, okay, so 1 over x, the graph goes positive and negative infinity. So when I put in sine of, let's say, infinity, right, because x is getting really close to 0, my sine function is moving really, really quickly. That's for sine infinity. It's going here and it's moving really quickly, like and it just keeps oscillating. So as I go to infinity, and the same thing is true when I go to negative infinity. Now that statement is happening at 0, meaning this is becoming like sine of positive and negative infinity when I'm getting closer and closer to 0. So what will happen is it will go like this, and it will start oscillating here really, really quickly. And that's what's happening. So just drawing clearly, it would go like this, and over here it oscillates back and forth really quickly as you hit 0. Really, really quickly starts oscillating back and forth, and it's important to understand why, but this is pretty much why. And the pi doesn't really change anything, so this is kind of what this part of the function does. So now the question is, what does this part of the function do? And the answer is it creates an amplitude, right? If you have a times sine of x, the amount that the function goes up and down, so sine is bounded, sine itself is bounded by 1 and negative 1. If, let's say, a is 10, then sine is bounded by negative 10 and 10. It basically changes how this amplitude changes. Now it's a function, but the function still changes the amplitude. But how can we find the limit of this function? So we can say, listen, sine of pi over x, like anything, like any sine function, which only has stuff going on inside over here, is bounded by negative 1 and by 1. So, and at the same time, the square root of x to the third plus x squared is never negative. It can't be negative. It's always a positive number. So we can just multiply everything by this without changing the equality sign. So we'll get negative x to the third plus x squared is less than square root of x to the third plus x squared sine pi over x is less than x to the third plus x squared. That's how we're going to squeeze our function. So this is going to be f of x, this is g of x, and this is h of x. Now the limit, so over here, the limit, and you can graph this to see that this is really true, and it really squeezes the function. Now the limit as x goes to 0 of our f of x, which is negative x to the third plus x squared, is equal to the limit as x goes to 0 of our h of x, which is x to the third plus x squared is equal to 0. Get from this that the limit as x goes to 0 of our problem, x to the third plus x squared times sine pi over x is equal to 0. And that is the answer to that problem. Problem 35, I'm not sure why they claim it's hard, but okay, so if you have So 35. Our question is, we have f 4x minus 9 is less than or equal to f of x is less than or equal to x squared minus 4x plus 7 for all x, and we want to find the limit as x goes to 4 of f of x. Well, this is pretty simple. Let's just, if this is true, let's just see what the limit as x goes to 4 of this function, call it g of x, and call this h of x, function g of x, hope that it's equal to the limit as x goes to 4 of h of x, and if it is, then that will be equal to the limit that as x goes to 4 of f of x, and we will be done. So let's see. So the limit as x goes to 4x minus 9 is equal to 7. And the limit as x goes to 4 of x squared minus 4x plus 7, right? These are going to cancel. It'll be 16 minus 16 plus 7. It's going to be 7. So the limit as x goes to 4 of f of x will be 7. Straight out of the squeeze. Next problem. So now problem 36 is the same. Problem 37 is kind of what we have been doing. Cosine 2x, right? We can say that cosine of 2 over x is greater than -1 and less than 1 for all x. And this is always positive, x to the 4th, so we can say negative x to the 4th is always less than x to the 4th cosine 2x. It's always less than x to the 4th. The limit as x goes to 0, right? We're looking for the limit as x goes to 0 of this. The limit of as x goes to 0 of negative x to the 4 is equal to the limit as x goes to 0 of x to the 4 is equal to 0. And so the limit of this is equal to 0, and that's how you prove it. Okay, so now let's do problem 39, which asks us for the limit as x goes to 3 of 2x plus the absolute value of x minus 3. Anytime you're dealing with a limit and an absolute value, you have to write down the definition of the absolute value and work like that. So what does the absolute value of x minus 3 tell us? So it tells us that it's x minus 3 straight up. So x minus 3 absolute value is equal to x minus 3 if x is bigger than 3. If x is bigger than 3 or equal to 3. And it is, right, because then this is going to be positive. And it is negative x plus 3 if x is less than 3. So if x is less than 3, you just take negative x minus 3. We opened it up, and so that's what it is. So let's look. So what we want to make sure here, the reason the limit might not exist is the limit of as x approaches 3 from the left must always equal the limit as x approaches 3 from the right if the limit exists. So let's make sure that they're the same. So let's look at the limit as x approaches 3 from the left. So this is equal to 2x, and let's see if we can just write out what the absolute value is. So if x is approaching 3 from the left, then x is smaller than 3. So x is smaller than 3. So this is just going to be equal negative x plus 3. Right? That's if we approach from the left. Now we can plug in what x is, and we're just going to get, this is going to equal to 6, because these are going to cancel. And the limit as x approaches 3 from the positive side is 2x, and now x is greater than 3 because we're approaching from the right side, so we're going to use this, x minus x plus x minus 3. And now what we have is again 6. So our limit exists and our limit is 6. And you'll definitely see examples where, because of the absolute value, the limit doesn't exist. Actually, let's do one. I believe that for 40, the limit won't exist. Let's look at problem 40. So we are looking for the limit as x goes to negative 6, 2x plus 12 over the absolute value of x plus 6. So again, let's write out what the absolute value here is saying. So the absolute value of x plus 6, always do this, is going to equal to just x plus 6 if x is big. Sorry. I can't write it there. Let's try again. It's going to be, so again, let's do it down here. The absolute value of x plus 6 is equal to x plus 6 if x is bigger than negative 6, greater than negative 6, correct? Yes. If x is greater than negative 6, then this is going to always be positive, and it's going to be negative x plus 6 if x is less than negative 6, because if x is less than negative 6, then adding a 6 to it will not make it positive, so you have to take the negative in order to make it positive. So that is what our absolute value is saying. So now, again, what we're trying to check is that the limit as x goes to negative 6 from the left is equal to the limit as x goes to negative 6 from the right, and we will see that that is not true, actually. So let's do it. So what is the limit as we go from the left? So the limit as x goes to negative 6 from the left is, so we're going to do 2x plus 12 over, and now x is coming from the left, so it's smaller than negative 6, so we're going to use this definition, so it's going to be negative x plus 6. Okay, and we know that we can write the top 2x plus 12 is equal to 2x plus 6, so this is going to equal to 2x plus 6 over negative x plus 6, and these are going to cancel, right? And so we're going to be left with negative 2. So as we approach from the left, we are left with negative 2. Now as we approach from the right, remember we're going to be using this x plus 6. So we're looking for the limit as x goes to negative 6 from the right and let's just write in what we know at the top already is, so 2x plus 6 over, and just x plus 6 because we're coming from the right, so x is 6, and because that x is bigger than 6 for this, these two cancel and we're left with 2. So again, we have the limit as x goes to negative 6 from the left is equal to negative 2, and the limit as x goes to negative 6 from the right is equal to 2. These don't equal. Whatever. And so the limit does not exist. Let's do problem 42. So we have the limit as x approaches negative 2 minus the absolute value of x over 2 plus x. So again, the absolute value of x is defined as x if x is greater or equal to 0, and negative x x is less than 0. So let's see the lim as x goes to -2 from the left. So x is going to -2 from the left. So x is less than 0. I mean, it's going to be 2 minus that. It's going to be 2 minus x, which is plus, over 2 plus x. So this becomes 1. And for the other case, if we're coming from the right, it's still going to be 2 minus x, because that x is still less than 0. And so you're going to have the same thing, so the limit is 1. So now let's do 43 and 44. I mean, it's the same. Basically, the question is if the limit for 43 and 44 are the same, then the limit as x goes to 0 of that function, 1. So, 43 is just basically, does the limit of x going to 0 of 1 over x minus 1 over the absolute value of x, does this limit exist? So we're going to do it from the left, which is question 43, and we're going to take the limit from the right, which is question 44, and we'll see if they're the same. And I assume they're not. So this is going to equal, so let's do it from the left first, and let's find the common denominator. So this is going to be equal the absolute value of x minus x over x times the absolute value of x. So, and now we're taking lim as x comes from the left. So when we're from the left, x is less than 0, and remember the absolute value of x is defined as x if x is greater than 0, and negative x if x is less than 0, greater or equal. So we are from the left, so x is less than 0. So this becomes negative x minus x over, and then that becomes, so negative x squared. That's what we get. So this is going to be negative 2x over negative x squared. These are going to cancel, so this is going to be negative 2 over negative x. So now we're approaching from the left. So the x over here is negative, and it's really small. Over here we have a constant, so we have a negative constant, which is 2, over a negative of a really, really small negative epsilon. Again, epsilon is really, really, really small. We're getting really close, so we're getting really small. And so this is the same as negative 2 over just epsilon, right? And we're taking the limit as epsilon is going to 0. I'm just putting in something else for x, and we're saying it's getting really small. And now this is now coming from the right, meaning epsilon is positive. So this goes to negative infinity because we have a negative over here. This is very small, so this goes to negative infinity. So this limit from the left is negative infinity. Let's see what the limit is from the right. So we have the limit as x goes to 0 from the right, 1 over x minus 1 over the absolute value of x is equal to the absolute value of x. So it's equal to absolute value of x minus x over x absolute value of x. But now x is positive, so we can just get rid of the absolute value. So this becomes x minus x over x squared, which is the same as 0, straight out 0, over x squared, the lim as x goes to 0 from the right, and this is just going to be 0 because there's a 0 over here, and even though this is approaching 0, it's never actually 0, it's just a limit. So for any given epsilon, no matter how small we get, for every x, no matter how small this x is getting, it's still some positive number, and so this becomes 0. And right, we're approaching from the right. So again, the limit as x goes to 0 from the left, 1 over x minus 1 over the absolute value of x is equal to negative infinity, and the limit as x goes to 0 from the right, 1 over x minus 1 over the absolute value of x is 0, and these are not equal, and so the limit does not exist. So the next problem we're going to do is problem 46 on page, again, 85. So we have this function f of x equals 4 minus x squared for x less than or equal to 2, and x minus 1 for x greater than 2. That's our function. So we want to find the limit as we approach from the left, from the right, and see if the limit as we approach 2. So what's the limit as x approaches 2 from the left of f of x? What's the limit as x approaches 2 from the right of f of this is left, this is right, that's left. And what's the limit as x approaches 2? Does this exist of f of x? Does this exist at all? So as we're approaching 2 from the right, we have that x is bigger than 2, right? So here's, let's say, 2. We're approaching here. X is bigger than 2. So when x is bigger than 2, we're looking at x minus 2. So we're going to have x minus 2 at minus 1. Plug in the 2, and we get 2 minus 1 equals 1. So the limit, the limit as we approach 2 from the right is 1. As we approach from the left, x is smaller than 2, so we're using 4. So we get 4 minus x squared. We get 4 minus x squared. So when we plug in a 2, we get 4 minus 4 equals 0. So this limit doesn't exist because as we approach from the right, we get 1, and as we approach from the left, we get 0. Yeah, so the limit doesn't exist. So now let's sketch the graph. So when x is bigger than 2, let's say 2, we have a line. This line intersects the y-axis. So when x is 0, this line is negative 1. It's here, and it's basically, and we know that at 2 it's 1. So the line would theoretically go something like this, but we don't want the dotted lines in our graph because this function f of x only starts being x minus 2 over here at 2. So then we have our line. Whatever. Let's see if I can erase some stuff. No. Okay, here. Whatever, I'm going to erase the whole thing. So we have the dotted part, but that's not part of our line. We get up to 2, and then we just have our line. And when we are smaller than 2, so we have our y-intercept is 4, and then we have a quadratic equation, so we have something like this, and we know that at 2, this hits 0 right there. So this is how our function looks. It goes like this, hits and at 2 it jumps to 1 and continues. Very nice. Okay, the next problem I'm going to do is problem 47. And again, we need to, so the problem is, I'm going to use a little f. F of x equals x squared minus 1 over the absolute value of x minus 1. So what's the absolute value of x minus 1? I'm going to give myself more room. The absolute value of x minus 1 is equal to x minus 1 if x is bigger than 1, right? If x is greater or equal to 1, then taking away a 1 from it will keep it positive, and it's going to be equal to negative x minus 1 if x is less than 1. If x is less than 1. Okay, so now let's find the limit for this thing. We need to find the limit. So we're looking for the limit as x approaches 1 from the left and from the right of x squared minus 1 over the absolute value of x minus 1. So let's find the limit as x approaches 1 from the right of x squared minus 1. So what goes on the bottom? So if you're approaching from the right, x is bigger than 1, so we're going to use this, x minus 1, right? And this is equal, so x squared minus 1 is the same as x minus 1 times x plus 1, right? Because this is x squared plus x minus 1. So this is equal to x minus 1 times x plus 1 over x minus 1. These cancel, and I put in a 1, so this is equal to 2. So as I'm approaching from the right, I get a 2. As I'm approaching from the left, we're going to use this, so it's the same thing. We're going to get to the limit as x approaches 1 from the left over here of x squared minus 1. Okay. X squared minus 1 over. Now we're using this, so we get negative x minus 1. So this is going to equal to x minus 1, x plus 1 over negative x minus 1. These cancel, and I get negative x plus 1, or when we plug in the 1, negative 2. And because that the limits are different as we approach from the left and the right, we claim that the limit doesn't exist. And now the graph would look something like this. So let us so we can look at, so we know that as I'm approaching x, so when x is less than 1, so if x is less than 1, then we have x squared, x squared minus 1 over negative x minus 1, which is equal to x plus 1 x minus 1 over x minus 1 negative. These cancel, and I get that my f of x when x is less than 1 is the same as negative x minus 1. So this will look something like, okay, so here's my graph, and here's 1. So when I'm smaller than 1, when x is smaller than 1, my x my y-intercept is at -1, so here it is at -1. And when I reach 1, I'm at -2, so here I'm at -2. And now this is a line with the slope of the line being 1 or -1. So it's a line that goes something like that. So this is when I'm smaller. Now when I'm bigger, if x is bigger than 1, f of x equals, and then by the same logic, we get, now we get x plus 1. So my intercept is going to be here, but again, this is at 1. This is dotted because this is not included in our function because this over here is still less than 1. And then I'm going to have a line. And this is at 2. Then I'm going to have a line like that. So this is how my function looks. Okay. Now let's do 48. Problem 48 on page exercise, let's say, on page 86. So we are given a function g of x equals, and this is going to be x if x is less. I'm just not going to put any of the ifs in. I don't think I have been until now. It doesn't really matter. If x is less than 1, 3 if x equals 1, 2 minus x squared if x is greater than 1 and less than or equal to 2, and x minus 3 if x is greater than 2. So now let's start evaluating our limits. So the lim, first question, the lim as x goes to 1 from the left. So if we're approaching from the left, x is less than 1, so we are dealing with this equation. So this is, we're just going to plug in 1 into x, and we get 1. So so for the first question, we get 1. As we approach, now what's the lim as x approaches 1 from the right? So if we are approaching from the right, we're greater than x, than 1. X is greater than 1 but less than 2. So we're going to use this equation. So it's going to be 2 minus x squared. Plugging in a 1, this is going to be 2 minus 1, which is 1. So these limits are the same. And then we have the limit as x approaches that's not a question. So there isn't a question about the right, but there is the question about the limit as x approaches 1, and because that the limit as x approaches 1 from the right is equal to the limit as x approaches 1 from the left is equal to 1, we get that the limit as x approaches 1 from 1 is also equal to 1. So that's the answer for the second thing. What is just g of 1? So g of 1 is exactly when x equals 1. So now we're using this one. So this is going to equal 3. The limit as x approaches 2 from the left. So the limit as x approaches 2 g of x from the left is equal to, so if I am at the left of 2, then I am less than 2, then x is less than 2 but greater than 1, so we're dealing with this case. And now we're just going to plug in this. So this is, so g of x now is 2 minus x squared. Plugging in a 2, we get 2 minus 4, which is equal to -2. So that's when we approach from the left. When we're approaching from the right, we have this. Plugging in a 2, we get 2 minus 3, and this is equal to -1. And because of that, for the last question, what's the limit as x approaches 2 of g of x? Well, it does not exist. because that there's a difference between approaching from the left and approaching from the right, as we just saw. So that's that. And now let's sketch our graph. So let's write down g of x again. G of x equals x 3, 2 minus x squared, x minus 3. This is if x is less than 1. If x is equal to 1, it's 3. Then we have if x is greater than 1 and less than or equal to 2. And then we have x is greater than 2. So let's start with x being less than 1. So here's our graph. Here is 1, and here is 2. So if x is less than 1, we just have x. So we're going to have this. Oh, sorry, wrong way. Okay. So when we have less than 1, we just have this going to 1. Now so then we go over here. At x equals 1, we are going to jump to 3. So this is at x equals 1, we jump to 3. At x now, as we saw before, when we approach 1 from the right and from the left, we get the same exact number. So for x between 1 and 2, we're basically going to start here, and we're going to start like that. We're going to have a quadratic form equation going down, and then we're basically going to go down until we hit 2 over here. And as we saw, our limit when we approach from the left over here was -2. So over here we have -2 right when we hit 2. And then when we're greater than 2, so when we are greater than 2, we get a line. Sorry, the line does not start there. It starts, when it starts, we know that, so at -1. So right here, at -1, let's say, our line starts, and then we just have a line like that. So that's how our function looks. Okay, next problem we're going to do is so the next problem we're going to do is problem 52. In the theory of relativity, the Lorentz contraction formula L equals L0 square root times the square root of 1 minus V squared over C squared. This is the length of an object, where L0 is from an observer with respect to some observer, where L is the length of that object if it were not moving, and C is the speed of light, and V is the velocity at which the object is going. So the question is, so what's the limit as V goes to C from the left, approaches C from the left, the speed of light, so our velocity is approaching the speed of light of L. Well, this is equal to the limit, so V approaches the speed of light from the left of L0, 1 minus V squared over C squared. And as we approach C from the left, this becomes L0 square root of 1 minus 1, because that V squared over C squared gets closer and closer to 1 as V goes to the speed of light, which is then equal to 0. So the lim, as V gets close to the speed of light of L, is equal to 0. So the object will have length 0. So the faster you go, the smaller the object will look until it doesn't have a length at all. And then the question is, why is the left-hand limit necessary? And well, for us it would be necessary because that if it were not, well, we cannot go faster than the speed of light, so you cannot really approach C from the right. The question is it, I don't know, is it mathematically necessary? It probably is, simply because otherwise you're going to have L0 times the square root of some really small negative number, because it will be 1 minus V squared over C squared, where this number is a little bigger than 1, right? And so, but then we'll be in the complex field, meaning this won't be a real value, and so we will be dealing with imaginary numbers. So maybe that's why C has to be less than, V has to be less than C, or has to be approaching from the left. But yeah. Okay, I'm just going to do problem 53, even though it's a proof, just quickly, for the fun of it. So we can use the following rules. We know that the limit as x goes to a of xn equals a n. That we know. And we know we can take out constants. So, and we also know that the limit as x goes to a of cfx equals c limit as x goes to a of fx. And because of this, so the question is, if p is a polynomial, show that the limit, so we're assuming p is a polynomial, show that the limit as x goes to a of p of x equals p of a. Well, so any p of x, if it's polynomial, can be written in the form a n x to the n plus a n minus 1 x n minus 1 dot 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 plus a1x plus a0. This is how a polynomial is written. So if I take the limit as x goes to a from this side, it's going to be the limit from this side, the limit of all this. But these are constants, these are linear, these are additions, and we know that the limit, another rule, as x goes to a of f of x plus g of x equals, if they exist, if the limit of f of x exists and the limit of g of x exists, this is going to equal the limit of f of x plus the limit of g of x, assuming that the limit exists. But for us, okay, so this can be thought of as g1 of x, f1 of x plus times a constant an plus f2 constant f2 of x dot 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 plus a1 fn of x plus a0. Right, we can think about it like that, polynomial. So the f of x is, so like f1 of x is going to just be x to the n. f2 of x is x minus n minus 1, x to the n minus 1. fn of x is just going to be, have fn, yeah, 1, f1, f2, f3. This would probably be fn minus 1. And this is just going to be n minus 1. This is going to be x, just x. And so the limit of each one of these exists, because if I take the limit over here as x goes to a for any of them, what I'm going to get is I'm going to get, right, because we know that the limit as a approaches x, sorry, as x approaches a, of x to the n for any n is just an. That was one of our rules. So all of these limits exist. So what we get in the end, the polynomial, the limit as x approaches a for our polynomial is just going to be an a to the n plus an minus 1 a n minus 1 dot 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 a1 a n plus a0, and this is just equal to PA. So that completes the proof. So the next problem we're going to do is the next problem I'm going to do is problem 55, which asks the question. So I have the limit as x approaches 1 of f of x minus 8 over x minus 1, and we claim that this is 10. So the question is find the limit as x approaches 1 of f of x. Right? So this over here is the same as the limit f of x minus 8 over the limit of x minus 1. This is x approaching 1, x approaching 1, because we can put the limit there, and then the 8 doesn't really need a limit. And we're saying that this is 10. So then we move this to the other side. We get the limit as x goes to 1, f of x minus 8 equals 10 times the limit as x goes to 1 of x minus 1. And then this is just 0. We move the 8 to the other side, so we get the limit as x goes to 1 of f of x equals 8. And that is our answer. Okay, next problem is going to be problem 56. So we're going to do the same exact thing with the limit laws. So the question is the limit as x goes to 0 f of x over x squared equals 5. Find the following limits. So we want the limit as x goes to 0 of f of x, and the limit as x goes to 0 of f of x over x. So over here, this is the same. You can write the limit as x goes to 0 of f of x over the limit as x goes to 0 of x squared equals 5, or the limit as x goes to 0 of f of x equals 5 times the limit as x goes to 0 of x squared. This becomes 0. So we have that the limit of f of x is 0, so this is going to be 0. And now the question is, what is the limit of f of x over x? I don't believe we can really answer this question, because so if f of x equals, let's say, x, so this is satisfied. The limit is as x goes to 0, 0. And then over here, the limit as x goes to 0 of x over x is just 1. But let's say f of x is equal to 2x. So over here again, it's satisfied. But over here, we're going to have the lim as x goes to 0 of 2x over x. And now we get 2. So I don't think we can really answer this question in any meaningful way. Okay, now problem 57, which says, so f of x equals x squared if x is rational, if x x is an element of the rational numbers, and it's going to be, rational numbers is q, and it's going to be 0 if x is an element of the rational numbers. And we want to prove that the limit as x goes to 0 of f of x is equal to 0. So what happens over here is you have your function, and you have a bunch of rational numbers getting closer and closer to 0. You have a bunch of irrational numbers here getting closer and closer to 0. So if we zoom in over here, right, let's say zooming in, and so we're going to have like a bunch of, rational numbers, infinite amount of them, and a bunch of irrational numbers, again an infinite amount of them, all getting closer to 0. And the function is changing based on where you are. So for all the irrational numbers, the function is 0, and for all the rational numbers, it's following some like quadratic thingy. And over here, so it's going here, and then hits 0, and it comes back up. Does something like that, and we want to prove that the limit for this thing is 0. Oh, wait, before we continue, I want to go back to the previous problem. So I said over here that, isn't it? Yeah, I said over here that I'm not really sure how to figure out this last part, but there actually is a solution. And this is the solution. So because we know, so this is the solution. So now they ask the question, what is what's the limit as x approaches 0 of f of x over x? And because we know that the limit as x approaches 0 of f of x over x squared is equal to 5, we know that f of x is going to 0 almost as quickly as x squared is going to 0. It's actually going to 0 a little faster. That's why we get a 5. So f of x is something in the form of like 5x squared, something like that. And it's moving a little faster towards 0, but it's in like basically the same rate, which means that when f of x is being divided by x, it's moving much, much faster towards 0. So let's say f of x is of the form 5x squared over x. These are going to cancel, and then the limit as x goes to 0 if this is 0. So the answer over here is 0, because that f of x is moving, even though x is going to 0, f of x is going towards 0 much faster, at a faster rate. It's going to 0 on the rate of like x squared, and so when it's only being divided by x, we're going to get a 0 over here. Okay, now back to this proof. So we can take our f of x, and squeeze it by the following. So we have x squared, negative x squared is, we don't even need that. 0 is always less than or equal to f of x, which is always less than or equal to x squared, right? Because that f of x is going to be most x squared, and this happens on the rational numbers, and everywhere else it's going to be 0, meaning at the irrational numbers it's 0. So it's basically something like this, and also with like a bunch of zeros over here. So we can just squeeze it with x squared and 0. And because of this, we know the limit as x goes to 0 of 0 is equal to the limit as x goes to 0 of x squared. is equal to 0. And so by the squeeze theorem, we know that the limit as x goes to 0 of f of x is also 0. That completes that proof. Now the next question we're going to do is question. So the next problem we're going to do is problem 58. And the simplest solution to this is taking f of x equals 1 over x and g of x equals negative 1 over x. For neither f of x nor g of x do we have, so the limit as x approaches 0, if we want a to be any number, we'll do this differently. But let's first say 0, if we want no, I don't know, yeah, we need a specific number, so we're going to have 0. So the limit as x approaches 0 of f of x equals, in a way, the limit as x approaches 0 of g of x, and it does not exist. But the limit as x approaches 0 of f of x plus g of x is equal the limit as x approaches 0 of 1 over x minus 1 over x, which is equal to 0, and so that limit exists. Okay, next problem. So now I'm going to do problem 59, and it says, show by means of an example that the limit as x approaches a of f of x times g of x might not exist, even though the limit as x approaches a may exist, even though the limit as x approaches a of f of x equals the limit as x approaches a of g of x, or that really does not exist. So if we take f of x to equal 1 over x and g of x to also equal 1 over x, we get that the limits for both of these don't exist. So the limit as x approaches a 0, the limit as x approaches 0 for both of these does not exist. But at the same time, the limit as x approaches 0 of 1 over x squared is plus infinity. If we want g of x to be different than f of x, we can say f of x equals 1 over x, g of x equals 1 over sine x, and we'll have the same result. The next problem I'm going to do is problem 61. This is again on page 86. So we want, is there a number a? So is there a number a such that we have the limit as x goes to negative 2 of 3x squared plus ax plus a plus 3 over x squared plus x minus 2, that this limit exists. Well, if you look at the denominator, you'll get, and you plug it in, you get that this is going to be 0 if you plug in 2. So the only way for this limit to exist, it's going to be 0, and also as we approach 0, it's going to be either negative or positive, because this number will count less than this number, than this x, and so depending on whether you're coming from so as you approach negative 2, depending on whether you come from the left to the right, sometimes this whole number will be negative, and sometimes this whole number will be positive. If it was only positive, then we might have a limit going to infinity. But now we have the denominator going to 0, but being slightly positive from one side and slightly negative from the other. So again, let's write this out, x squared plus x minus 2. So because of this, the only way for this limit to exist, meaning if in the numerator you had a number greater than 0, then this won't exist. It will go to plus and minus infinity. So the only way for this to exist is if in the numerator we have 3x squared minus ax plus a plus 3 equals 0. That's the only way for this to happen. And we want this to equal to 0 when we plug in a negative 2. So we want 3 times negative 2 squared minus a negative 2 plus a plus 3 to equal to 0. Or in other words, we want 12 minus, so plus 2a, so plus 3a plus 3 to equal to 0, or in other words, what we want is 3a plus 15 to equal to 0. Wait, I'm sorry, this should be positive, and this should be positive. Yeah, maybe. Yeah, those should be positive. So this is positive. So this is incorrect. Now we're going to have 12 minus a plus 3 equals 0, or negative a equals negative 15, or a equals 15. So when a equals 15, this limit exists. And what that limit is, I don't know. I'm not going to find out. But it does exist. Oh, if so, find the value of a and the value of the limit. I am going to do this with L'Hopital's rule. If you know what it is, then good. If not, then I don't know. Trust me on this one, I guess. So we're gonna have, so what's the limit? We're looking for the limit as x goes to negative 2 of 3x squared plus 15x plus 15 plus 3 over x squared plus x minus 2. If you know L'Hopital's rule, you take the derivative of the numerator and denominator. So this is going to be 6x plus 15 over 2x plus 1, and then where are we going to do it again? I don't think so. So the limit as x goes to negative 2. We plug this in. This is going to be negative 2. This is going to be a negative 3. And this is going to be negative 12 plus 15, which is equal to 3 over negative 3, which is equal to negative 1. So the limit is negative 1. And we did that with L'Hopital's rule. Definitely something that everyone should learn before the end of Calc 1. But we haven't done derivatives yet, so whatever. So the last problem I'm going to do in this video thingy is problem 62. You don't have to know this problem, I'm pretty sure. It's just a cool problem, so I'm going to do it. And if you want, you can stay and watch, and otherwise, you don't have to. So we have this graph. We have a circle, a point P, another circle. We'll be really bad at this, but okay, fine, kind of worked. And the point of intersection we're calling Q, where they meet. And this circle is C2, this circle is C1, this is 0. And we're going to draw a line from P to Q. and then it's going to intersect the x-axis right there, and we're calling that r. And the question is this: so the circle C1, so C1 over here is given with the equation x minus 1 squared plus y squared equals 1. That's the point, that's C1. And the second circle, C2, is shrinking, so it's shrinking and shrinking and shrinking, and it's going to end up just being a dot right there. And so, but C2 is given by the equation of the normal circle x squared plus y squared equals r squared. And the question is, what is the limit as r goes, where is this point? Right, when we create this line by the method of finding the upper point in C2 and the intersection between C2 and C1 and just drawing a line between them and seeing where they intersect the x-axis. But as we make C2 go down to this little point, we shrink it, meaning we make r for C2 go down to 0. Where is this point going to be? Now, when we're exactly at 0, we're just going to have a line here, and we're going to intersect the entire x-axis. But we want to know if, like, I'm a little bit bigger, and I still kind of have an intersection, I make a point. What point am I really close to over here? What point am I, and where's my limit? So the way to do this is to find the function for this line. The way to do that is to find where Q is and where P is, and to use that to find the slope of the line or something like that, and then to use that information to determine this line, and then take the take r to 0 something. So the point P is very easy to determine. It's just 0 comma r, right? Because it's right, the point right over there, so it's 0 comma r. Point Q will be a little more difficult to determine, but it's in the intersection of this circle and this circle, so it's where, when this, we wish to find what Q is. So first, so our other equation was what? X minus 1 squared plus y squared equals 1. So let's just solve for x first. So this gives us y squared equals 1 minus x minus 1 squared. And we have that there. And from this equation, we get y squared equals r squared minus x squared, right? Yes. Right. So now we want to set them to equal each other. So we get 1 minus x minus 1 squared equals r squared minus x squared. So now, in order to solve for x, so what is x minus 1 squared is the same thing. Okay, so x minus 1 is x squared minus 2x plus 1. So we get, so this is going to give me 1 minus x squared minus 2x plus 1 equals r squared minus this minus goes over here, minus x squared, right? So now we have 1 minus x squared plus 2x minus 1. So equals, so let's just say equal minus 1 minus r squared plus x squared equals 0, just moving these two to the other side. These cancel, and we get, we're gonna get, this is squared, we're gonna get, okay, so 2x equals r equals, this should be a negative, so 2x equals r squared, or in other words, x equals r squared over 2. So, okay, so that's the first thing, x equals r squared over 2. And now we can plug it back into our original equation, right? Because we know that x squared plus y squared equals r squared. That's our original equation for C2. So we plug this in, so we get r squared over 2 squared plus y squared equals r squared, or in other words, 2y squared equals r squared minus r to the 4th power over 4, right? So, or this equals r squared 1 minus r squared over 4. So we get that y equals the square root of this, which is r square root of 1 minus r squared over 4. So the coordinates for our p, again, is 0, r. The coordinates for our q, we have, for x, we have r squared over 2, and for y, we have r square root 1 minus r squared over 4. That's what we have. Okay. So now the slope of our line PQ is going to be, this minus that, so r times the square root of 1 minus r squared over 4 minus r, divided by this minus that, so r squared over 4 minus 0. This is equal to m. And now, in order to find our line, we choose a point with this. So we have y2 minus y1 equals m, x2 minus x1. This is the equation for our line. So for us, we're going to have y minus, and for y1, let's just choose r equals, and then for the m, we have r square root of 1 minus r squared over 4, r squared over 4 minus r over r squared over 4 times, and then x2 is just going to be x, and then minus 0, because that's right, because we chose the point, chose to do this with the point P equals r 0, really 0 r. So that's the equation of our line, and our line intersects the x coordinate when y is 0. So let's take y equals 0. So this is so this is where we intersect the x coordinate in the general way of where x intersects the x coordinate. So let's just solve for x. So we have x equals negative r over this slope over here, which is so r times 1 minus r squared over 4 minus 1, I'm just taking out the r, over r squared over 4. So this is what we get. So now what we have is, so this is the same, remember if we have a over b over c over d, this is the same as dA over bc. So this is the same as negative r times r squared over 4 divided by r square root of 1 minus r squared over 4 minus 1. So we get this, these cancel. So what we get is negative r squared over 4 times, and then negative r squared over 4 times square root of 1 minus r squared over 4 and oops, wrong way, and then plus, oh sorry, this one, minus 1. Okay, so now let's multiply both of these by the conjugate of the denominator. So we're going to get times the square root of 1 minus r squared over 4 plus 1 divided by 1 minus r squared over 4 plus 1. So what is this over here? So it's going to be the square root of 1. So basically we're going to get 1 minus, because this is just going to get squared, and then when we take this times that, we're going to get a plus. When we take that times that, we're going to get a minus. They're going to cancel, and then we're going to get a negative 1 over here. So it's going to be 1 minus r squared over 4 plus 1, right? Yes, 1 plus 1, these are going to cancel, so I'm going to get r squared over 4. That's what we're getting in the numerator. So we're going to get, so this is going to equal to negative r squared over 4 times the square root of 1 minus r squared over 4 plus 1 divided by r squared over 4. These cancel, so I get negative square root of 1 minus r squared over 4 plus 1. So this is the x-intercept of my line. I just realized I made a mistake. Right, when I was finding the slope, this should be a 2, because yeah, that's a 2 over there. That's 2. And then this is a 2. And a few other changes must be made, I guess. I don't know. Yeah, this is a 2. And then you see, so now this is a 2. So now it's going to be these. This is going to be a 2. This is going to be a r squared over 4. So what's going to happen? So you're going to be left with 2 times this over here. Yes. And over here we have a negative, so over here we have a negative, so the negative vanishes, so there's no negative over here. Okay, so now so this is for any r, the x-intercept, so for any r, the x-intercept is 2 times 1 plus 1 over 4 minus whatever, 1 minus 1 over 4 r squared plus 1. This is for any any intercept. So now when we take the limit as r goes to 0 of this thing, we get, so this goes to 0, and we just get 2 times 1 plus that, which is equal to 4. So the limit of this intercept is 4. And I think that the next, I'm going to basically have, the next video is going to be about the epsilon delta definition, and I'll just go through a bunch of examples regarding the epsilon delta definition. Okay, hope you enjoyed.